Recording is rolling. Welcome to Tuesday, May 2nd. So we're going to continue with quantum journals. Actually, I want to go ahead and wrap these up today. Right. So I'll cut a couple of things, move things on a bit fast. But yeah, we're going to wrap these up today. I'll have you guys just turn this in. Because again, I'm not going to see you guys the next couple of days. And then Friday is going to be a different kind of day. So yeah, we'll do that. Oh, announcement from administration. If you think you might be failing due to absences, then pick up an FA packet at lunch. Okay, right? You guys see that? Right. Oh, so next couple of days. Right now, I'm making a video for all my classes, so this is a unique based on class. But you guys see where you're going to be tomorrow, right? Great. Now, my first 4 classes are relocating, so my 6th and 7th periods will be in here, but my first 4 are relocating. Now, this is for Wednesday, so that's tomorrow, Wednesday. Now, the day after on Thursday, I'm proctoring another exam. So we've got these relocations. Okay? Right, so I will post these flyers around in the halls. They're in yesterday's video already recorded, and they're being recorded right now. So you guys have all these different places where you can find these relocation information. Okay. All right, you guys get there? All right, let's get going on quantum journals. Quantum journal. All right, so the last one we did yesterday, we were looking at this the Higgs field and the Higgs boson, and like where does math come from a particle physics point of view. Okay, let's flip over to Feynman diagrams. Feynman diagram. Actually, this is one of my posters right here. You know what? Let's do this. Let's just copy down this one from my poster, and then I'll flip my screen and we'll look at some other ones too. Okay, but Feynman diagram. This is a diagram that you can use to show a particle collision. Remember, we've been talking about particle colliders for last couple of days. Okay? So typically, you put time on the vertical axis and a spatial direction on the horizontal axis. So I'll put time here and space here, right? Which is opposite of what we did all fall semester. But I guess in particle physics and relativity, they flip some axes for different. Okay, and then we've got these different kind of particles. So I have a pretty basic Feynman diagram going here. I got 2 electrons that are headed towards each other in space as time's ticking along. Okay, so I've got 2 electrons headed toward each other, electron, electron. Okay, and then they'll collide, release a photon, and then bounce away as these antiparticles of what are called positrons. Right, so see. Like E plus. So this could look like an electron, except it has a positive charge and also has like a negative mass. So it's actually an antiparticle is what this is. And see how like the arrows are pointed in the opposite direction of time? Right? That's a convention for an antiparticle. Right? They're not moving backwards in time. Well, at least the way I'm interpreting it. Right? But those are called positrons there. Right? So key. I'm going to copy down this key. So whenever you see a solid line, that refers to some kind of fermion, which you guys remember from yesterday includes quarks and leptons. An electron is an example of a lepton. If you see a wavy line, right, that is a photon. Right, gets its own symbol. Right. If you see like a curly, right, as a gluon, it's related to the strong force that holds the nucleus together. And if you see a dashed line, that's some other kind of boson. Right? Oh, like yesterday, we're looking at the Higgs boson, for example. Dashes, like that. Okay. All right. So you guys got that Feynman diagram? All right. So I flip my screen over. Share screen 2. Dig up the video that want. This. All right, so here's the last one you saw yesterday. I showed you guys the 3-part on Higgs boson, and near the end, they flash a bunch of Feynman diagrams. Let's see if I can find them. Here we go. Here we go.
Them, and that's just to check if a 20-sided die is rigged. There are far more than 20 possible outcomes of.
Yeah, you guys see all those different Feynman diagrams. Like there's one there, right? Right. Okay, so that's fun. Right, next one. Oh, Got hey guys. Oh, did you miss the you thought the relocations were today? Is that okay? Here, I'll get you guys in here while I'm playing quantum computing. All right, so we're just continuing on quantum mechanics. Yeah, maybe I showed you guys those relocations too early.
A classical computer performs operations using classical bits, which can be either 0 or 1. Now, in contrast, a quantum computer uses quantum bits, or qubits, and they can be both 0 and 1 at the same time. And it is this that gives a quantum computer its superior computing power. There are a number of physical objects that can be used as a qubit: a single photon, a nucleus, or an electron. I met up with researchers who are using the outermost electron in phosphorus as a qubit. But how does that work? Well, all electrons have magnetic fields, so they're basically like tiny bar magnets. And this property is called spin. If you place them in a magnetic field, they will align with that field, just like a compass needle lines up with the magnetic field of the Earth. Now, this is the lowest energy state, so you could call it the 0 state, or we call it, for the electron, spin down. Now, you can put it in a 1 state or spin up, but that takes some energy.
If you took out the glass from your compass, you could turn the needle the other way, but you would have to apply some force to it. You have to push it to flip to the other side. And that is the highest energy state. In principle, if you were so delicate to really put it exactly against the magnetic field, it would stay there.
Now, so far, this is basically just like a classical bit. It's got 2 states, spin up and spin down, which are like the classical 1 and 0. But the funny thing about quantum objects is that they can be in both states at once. Now, when you measure the spin, it will be either up or down. But before you measure it, the electron can exist in what's called a quantum superposition, where these coefficients indicate the relative probability of finding the electron in one state or the other. Now, it's hard to imagine how this enables the incredible computing power of quantum computers without considering 2 interacting quantum bits. Hello. Hi. Now there are 4 possible states of these 2 electrons.
You could think that, well, that's just like 2 bits of a classical computer, right? If you have 2 bits, you can write 0, 0, 0, 1, 1, 0, 1, 1. Right? There's 4 numbers. But these are still just 2 bits of information. Right? All I need to say to determine which one of the 4 numbers you have in your computer code is the value of the first bit and the value of the second bit. Here instead, quantum mechanics allows me to make superposition of each one of these 4 states. So I can write quantum mechanical state, which is perfectly legitimate, that is some coefficient times this, plus some coefficient times that, plus some coefficient times that, plus some coefficient. So to determine the state of this 2-spin system, I need to give you 4 numbers, 4 coefficients. Whereas in the classical example of the 2 bits, I only need to give you 2 bits. So this is how you understand why 2 qubits actually contain 4 bits of information. I need to give you 4 numbers to tell you the state of the system. Whereas here I only need 2. Now, if we make 3 spins, we would have 8 different states. I need to give you 8 different numbers to define the state of those 3 spins. Whereas classically, it's just 3 bits. If you keep going, what you'll find is that the amount of equivalent classical information contained by n qubits is 2 to the power n classical bits. And of course, the power of exponentials tells you that once you have, let's say, 300 of those qubits in what we call the fully entangled state. So you must be able to create these really crazy states where there is a superposition of all 300s being one way and another way and another way and so on. Then you have like 2 to the 300 classical bits, which is as many particles as there are in the universe.
Whoa. All right, so back over here. All right, assuming here you guys see this. All right. So yeah, if you walked in a bit late, the one you would have missed was Feynman diagrams, which I have a poster for. It's hanging from the ceiling right above me right here. Right, so that was number 18. But the video you guys just saw, quantum computing, is number 19. Okay, so hey, talking about bits versus these qubits for quantum computing. Okay? Now that whole video I just played you guys comes from a digital file, right? Like you get down to it, it's just a string of zeros and ones that the computer is interpreting and playing as a video file. Okay? That's all just classical computers, okay? But if you have a quantum computer, then you have the superposition state. So it's not a 0 or a 1. It could be 0 and 1 and then entangled state. Now to get the information out of it, you have to like unentangle it. But before you do that, it could be in this entangled state. It could be both a 0 and a 1. Okay? So if you run the think about how this could work mathematically, the fact that it could be both, right? N qubits contain 2 to the power of n classical bits of information. For example, if you have 3 qubits, 2 to the power of 3, that's like 8 bits of like classical information, right? Classical bits of information, right? 2, 4, 8, right? 2 times 2 times 2, right? Right. But because of how exponentials like scale up so fast, so quick, right? If you have just 300 qubits, again, this could be stored in materials, and this could be like 300 like phosphorus atoms, right? So this could be something that's like too small even for your eye to perceive, like 300 qubits. 2 to the power of 300 classical bits equivalent information, again, in the fully entangled state. We're talking about 2 to the power of 300 is the number of particles there are in the observable universe. So there's an enormous amount of possibility in just like even just a few, like a small number of atoms. Okay. What can you do with quantum computers? Well, this is an emerging technology, so it's not fully fleshed out at this point, but you guys have seen how fast technology has been moving along since before we were born, and even recently, some recent developments with AI that are now going to like, further accelerate technology. What could you do with quantum computers? Possibly crack a bunch of problems that are not solvable right now. There's a worry in some sense that this could override encryption, that you could just like decrypt anything because it could just run through all the combinations simultaneously. Passwords might be tricky in the future. All of us have passwords to different accounts, but what if you just bring in a quantum computer and it tests out everything simultaneously and just hones in on the right one, right? Right, so that's a possible thing coming in the future where like, passwords don't function the way they do today. So, but yeah, I guess like with any technology, right? There's good and bad things that come with that. Right, so are you guys ready for number 20? Maxwell's Demon and the Landauer limit. Right, so this one I do have a video for. It's a little lengthy, so I'm just going to explain it here because again, I'd like to try to wrap this up today. Right, I'm going to draw our 2 side-by-side tanks. Right? This is a thermodynamics idea that is going to relate to quantum. Right? Right? So 2 side-by-side tanks. Right? Well, okay, I'll start off with just an aquarium. Right? So I got my aquarium. Right? I'm going to put a partition down the middle. Right? Got a partition down the middle. Right? And let's say on one side I've got all hot water, and on the other side I got all cold water. Okay? Now, if you took the partition out, what you would naturally expect is that the hot and the cold are going to mix, and it's going to create just room temperature water, right? Back when we were studying thermodynamics, that was related to what was called the second law of thermodynamics, right? Which has to do with it. There's a time order of processes that will spontaneously occur. Entropy in the universe naturally increases, right, as time progresses, right? So hot and cold, you mix them, they're going to create room temperature. Great. If you started out with a big tank of room temperature water, you would not expect it to spontaneously divvy where the hot runs to the left side and the cold runs to the right side. Like that would be weird. That would actually break the second law of thermo, right? Now you could force that to happen. That's what air conditioning is. Right? That's what refrigeration is. Refrigeration is you start out with just room temperature air, and you run a process where you force it to separate, and then you dump the cold into the fridge, and you take the hot and just dump it out into the environment. That kind of simplified version of that process. But let's go back to the 19th century when, say, refrigeration was like just being developed and people were starting to think about ideas like this. This guy, James Clerk Maxwell, who did a lot of work with both thermodynamics and electromagnetism, he was thinking about this and said, hey, what if you had like some being that had like universal knowledge of particles? And I'm going to put that being perched on this partition. I called him a demon. I think the idea had to do with like this character would have knowledge that like humans maybe wouldn't have access to, right? Right. So I'll give him a little pitchfork and tail. How about that? Right. Got a little demon character there. Right. But again, what's special about this character is that he has universal knowledge about every particle in each of these tanks. Okay? And he also has control over a doorway in this partition. So he can open and close it. And maybe it's spring loaded. So whatever energy he expends opening it, he gets all that energy back by closing it. So there's zero net energy associated with controlling the partition. Right? And what he does is maybe it starts out as all just room temperature water, but he lets all the fast moving particles into the left side. And he lets all the slow moving particles into the right side. Now, if you remember kinetic energy theory of temperature, then you remember that if something is really hot, that's associated with like fast moving atoms, like fast vibrating atoms, fast moving atoms. And if something's really cold, then, well, the opposite, that's like slow moving atoms, right? So what this character has effectively done is he's created a refrigeration system, not expending any energy, but only using information. So here, let me jot down some stuff I just said. Right? So it allows fast particles to move to the left, and slow particles to the right. Right. Here's the key that really makes this interesting thing about, right? With only information, right? All he has is information about the motions of these particles. Right? So would this break the second law of thermodynamics? Okay. Remember, these are laws that were just being discovered and developed around like the 19th century, right? Then along comes James Clerk Maxwell and says, well, what if you had some character that had universal knowledge? Okay. Could he build a refrigerator next to, say, like a boiler using only information, right? And let's look at the hot side too, because I've been focusing on the refrigeration side, but that's only half the concept. What if this hot side gets so hot that it actually boils and creates steam? You could use that to turn a turbine, and that would be a power plant. So now this guy's built a fridge next to a power plant with no energy input. All he's using is information, right? Now, since we're in the 21st century, replace this demon character with a modern supercomputer, and this looks like a really enticing idea, doesn't it? Right. Now, scientists, physicists felt intuitively that there had to be something wrong with this. But it took them a long, long time to finally pin down what that was. And the reason that this doesn't work, right? The reason that the answer is no, you can't break the second law of thermo with only information, is because of what's called the Landauer limit. Landauer limit. Right. Now, the Landauer limit, there's a number associated with this. It's 0.018 electron volts of energy to erase 1 bit of information. Right. So going back to this demon character, right, or could be a modern day supercomputer, right? If this character is keeping track of which particles have what speeds, right, as he's trying to let the fast ones to the left and slow ones to the right, right? There's only so much storage space that he has to keep track of that information. And at some point he has to like either forget the information or delete the information to make way for more information so he can continue this process. And that deletion of information takes a tiny, tiny, tiny amount of energy. I mean, 0.018 electron volts, that's like so small, but it's not zero. And so that exchange of energy that's embedded in that information, okay, the increase in entropy that's caused by that exchange of energy outweighs the decrease in entropy that he gets by separating out the hot from the cold particles, right? The fast from the slow. Okay. So overall, the entropy of the universe increases, and the second law of thermo is still intact. Right? So the really like bizarre implication from this seems to be that information is necessarily embedded in physical systems that requires energy, right? So any thought that you have, any note that you write on a paper or erase, there's energy and entropy associated with just the fact that there's usable information there. Okay? Right, you guys got that? Right, so crazy ideas, but that's a fun one. All right, you guys ready for superconductivity? Okay, now this one I do have some slides for, but I'm gonna go ahead and draw this out first. We'll do this one kind of backwards. Explain this. So let's make a graph here. Do you guys remember the Plato lab you guys did a few weeks back where you were calculating what is the resistivity of Plato, right? Now, Plato was conductive. You could run electricity through it, like light up a bulb. Okay? So it acted kind of like a wire, like a copper wire or an aluminum wire. I'm going to put resistivity. We were using Greek letter rho to represent resistivity, okay? And the unit was ohm meters. Right? Although I've seen versions of this too. You can just put plain resistance and ohms here, right? So either way, okay. As a function of temperature in Kelvin, okay? Because that resistivity of that Plato, I think it was like 0.25 ohm meters or something like that. Okay? Actually depends on the temperature. So suppose you have a copper wire, maybe that's more conventional than Plato, okay? And you make the copper wire colder. It actually transmits energy better. That's to say the resistance or the resistivity of that material decreases. So back a little over 100 years ago, scientists were testing this out, and probably a copper wire, right, or whatever they work with, right? They made it colder and colder. That's like moving to the left, and they watched the resistance and the resistivity decrease, right? It was pretty linear. It's like, okay, so that's all fine and good. But then at some critical temperature, something totally unexpected happened. Nobody was expecting. Right? I'll call this TC, critical temperature. Suddenly, the resistivity of the material and the resistance in the wire dropped to like exactly zero. Right? 0 ohms of resistance, 0 ohm meters of resistivity. Right? And that is super conductivity. Right? So if you have some superconductive material, think about what that means. You can transmit energy with 0 energy loss, right? So be 100% efficient. Right? You could do something like have a wire in a loop and just run a current around it. I'll call it I for current, maybe some number of amps. And it could effectively store energy like a battery. You can do that indefinitely. Right? You can do a lot of things, really cool things with superconductors. Right? Now, the tricky thing with superconductors, though, is that this critical temperature is a really low temperature. What temperature are we talking about? Well, it depends on the material, so it's different for different materials. Right? But we're talking about like usually less than 100 Kelvin, which is like negative, like 400 some degrees Fahrenheit or negative 200 something degrees Celsius. So it's like crazy cold. Right? So how do you get something that cold? Well, now you need to like run refrigeration systems, and now it doesn't really, it's not really efficient to do that anymore. Right? So let me flip my screen over here. Right? And let's look at a couple of slides. All right, one is pretty much that graph I was just showing you guys. All right, you guys got that there? And the other one, I know what I'm going to do. I'm going to open this in a paint file because otherwise it like shows up transparent. All right, so here we go. So resistivity as a function of temperature. Okay, again, experiment, totally unexpected. All of a sudden, bam, this critical temperature, just look like barely under 100 Kelvin here. It drops to 0. Resistivity, got superconductivity. Okay. Another slide I have, just like some file was showing up transparent, so I have to open this in a paint file, is what is that critical temperature where it drops to 0 resistance, goes superconductive, okay? As a function of, for any particular material. So the first ones that were discovered were in, well, just after the turn of the century, like over 100 years ago, right? So we got mercury, we got lead, those were found to go superconductive. And then in the meantime, again, those are like less than 10 Kelvin. So that's like crazy cold. That's almost absolute zero, right? Okay. But jump up to like more modern day, like this century, and it looks like there was some material that was discovered to go superconductive even at like 200 Kelvin, which is still like sub-zero temperature in terms of like Celsius or Fahrenheit. So it's still actually wait, no, that's not true in terms of Celsius, is it? So no, that would be about actually, is this one room temperature? Hold on a minute. 373 K equals, huh?
Negative 67 Celsius.
Oh, sorry, you're right. Whoops, sorry, I didn't do the right in my head. Yeah, you're right. You're right. So that's still sub-zero in terms of like a Celsius system temperature. So it's still crazy cold, but it's like closer to room temperature. Now, is there some material out there that goes superconductive at room temperature? Open question. Still looking for it. Okay. Now, what's something cool you can do with superconductive materials? Quantum locking. So here's the next one.
The phenomenon you saw here for a brief moment is called quantum levitation and quantum locking. And the object that was levitating here is called a superconductor. Superconductivity is a quantum state of the matter, and it occurs only below a certain critical temperature. Now, it's quite an old phenomenon. It was discovered 100 years ago. However, only recently, due to several technological advancements, we are now able to demonstrate to you quantum levitation and quantum locking. So a superconductor is defined by two properties. The first is zero electrical resistance, and the second is the expulsion of magnetic field from the interior of the superconductor. That sounds complicated, right? But what is electrical resistance? So electricity is the flow of electrons inside the material. And these electrons, while flowing, they collide with the atoms. And in these collisions, they lose a certain amount of energy. And they dissipate this energy in the form of heat. And you know that effect. However, inside a superconductor, there are no collisions. So there is no energy dissipation.
Hey, look at that. That's about the graph I just showed you guys, right? You see that right there? All right, so let me zoom ahead a little bit. So he's talking about superconductors. Oh, look at that. You guys see that blue ball might represent a superconductor, but you guys see those field lines going around it? And they're labeled B. You guys remember B designates a magnetic field, right? So we got magnetic field lines, but the one on the right compared to the one on the left might just be regular material, right? But the one on the right, you guys see how those magnetic field lines are expelled? Right? That's one thing that a superconductor does, right? And they will also lock in place. Oh, there you go. Right, you guys see those like lock in place? Let me play a little
This
bit.
movie here, you can see how they flow one by one discretely. This is
right.
Strands of magnetic field.
Strands of magnetic field. See how they're like locked in place? Ah, they're like quantized, right? So they got these quantized magnetic field lines, right? All right, so let's see what happens when you put this all together.
Actually locking, three-dimensional locking of the superconductor. Now, of course, I can turn it upside down and it will remain locked.
Overjump that a little bit.
I can rearrange the flux zones and it will be locked in this new configuration, like this, or move it slightly to the right.
So he's got magnets down here, but he's got just a superconductor here, right? See, it sells all like smoky looking, right? Because you have that in, I want to say liquid nitrogen to keep it really cold, because of course you have to have it really cold for it to be superconductive, right? And that's all evaporating, right? So, all right, what else we got? Got some, here we go. Let's check out these cool demos.
Circular rail here. And when I place the superconducting disc on top of this rail, it moves freely. And again, that's not all. I can adjust its position like this and rotate, and it freely moves in this new position.
Let me find one more that he does here. Here we go, here we go.
Track. And hopefully, if I did it correctly, it stays suspended.
Pretty cool. All right, switch over here. And so And here's one fun property of superconductors, right? The fact that they will expel these magnetic field lines, right? Is calling these fluxons, right? So these are like quantized magnetic field lines, right? Feel locked in place, right? Then, yeah, right? They'll be locked in place like relative to those field lines. So, all right, you guys got that one? We got quantum locking. All right, let's do next one. How does a laser work? All right. It goes real fast. Got a minute physics lined up.
To make a laser, all you need to do is give a big collection of atoms enough energy so they're excited and ready to emit light. Once one of them spontaneously emits a photon, it'll stimulate some of the others to do so, and you get a nice cascade of illumination. But instead of letting all the light escape, it's more powerful to trap it between two mirrors and let it bounce back and forth through the atoms. All that passing light will stimulate them to emit even more light, and as long as you keep on re-exciting the atoms, they're happy to go on emitting light forever. But why do the atoms emit light just because another photon passes by? It's actually pretty simple. Imagine flipping two coins. They can either be in the same state or in different states. But photons aren't like coins. No matter how hard you try, you can't tell one apart from another. So in a photon flipping experiment, that means there's only one way for them to be in different states, but two ways for them to be in the same state. So they're more likely to be in the same state. And in general, this implies that photons always want to be like other photons, to have the same phase, polarization, and go in the same direction. And what's more amazing is that if a solitary photon passes by an excited atom that could emit another photon, there's a good chance it will emit one, because the two photons want to be together, even before the second one exists. So once you have all these friendly photons bouncing around between the mirrors, you can just open up a little hole at the end and let out a blinding stream of coherent light, a laser beam.
All right. All right. So, so if you have a couple of mirrors and let the light bounce back and forth, right, these photons here, just to recap on what he said here, right, the photons are more likely to be in phase than not, have the same polarization, right? Because again, this is a quantum mechanical effect. In quantum mechanics, particles are not readily distinguishable. Right? This is kind of where we started the story, or pretty close to it. Is what is light? Is light waves or particles, right? And has this dual nature. So you could talk about like photons as particles, but yeah, in quantum mechanics, well, they really have more wave-like properties too. Like same was true for like electrons, right? So is light more like a particle or more like a wave? And its wave properties makes it more likely that these photons will share characteristics. It's allowing for laser lights. All right. All right, you guys got laser. All right, this next one, Hawking radiation. I do have a video for this one. It's a little bit lengthy, and again, trying to wrap these journals up today. So you just go ahead and take care of this one myself. Go with you guys. Right. So suppose there's a black hole. So a piece of a black hole. So black hole. Right. Now black hole. Get too close to it, then everything pulls in. Like even light can't escape. Right. Has an escape speed greater than speed of light. Right. Now suppose you're sort of in the vicinity of this black hole, right? And you're looking at like the vacuum of space out here. Now, what is in the vacuum of space? You might say nothing. You might say, well, maybe there's little trickles of hydrogen atoms, right? Those might both be good answers in classical mechanics anyway. But then in quantum mechanics, there's also this effect of there are regularly popping up in and out of existence, particle-antiparticle pairs. I'm going to call this the antiparticle, and this guy the particle. Right. This is probably going on in this room right now, right? Where there's this particle-antiparticle pair that just pops up. One has positive mass and positive energy, the other has negative mass and negative energy. But then what usually happens is they just immediately annihilate each other, and then it's a wash as if it never happened at all, right? So out in the vacuum of deep space, this is going on all the time, right? And then, right, nothing too special. But what Stephen Hawking realized is that this antiparticle would not have enough energy to escape the black hole, whereas the particle possibly could, right? Again, if they're just the right position relative to the black hole, and it maybe has the correct speed, right? So the antiparticle will fall into the black hole, whereas the particle will sometimes escape out into the wider universe. Right here, let me jot that down. So the antiparticle falls into the black hole, whereas the particle can have enough energy to escape into the universe. Okay? And what this causes is for the black hole to eventually dissipate. Oh, and that particle escaping this whole system and flying out into the wider universe, that is the Hawking radiation. So this is the Hawking radiation right here. So does a black hole last forever? Well, if you're thinking just in terms of like Newtonian mechanics or even like general relativity, it seems like, well, all it does is accumulate more matter that can never escape. So the black hole can grow, but right, once you're in the black hole, it's just like trapped, and that's the end of the story. But Hawking radiation says, no, actually, because of this quantum mechanical process that happens in the vicinity of a black hole, and I think this is true, this has been observed to be the case, that there's this Hawking radiation that will leave the vicinity of the black hole. Okay? That those antiparticles are slowly dissipating that black hole. Now, it'll be a long, long time before the black hole dissipates. It might be like 1 trillion years or something on that order of magnitude. But hey, run the clock ahead enough time, and maybe universe will be around enough time to see something like that happen. Okay. All right, so you guys good there? All right, Hawking radiation. All right, next one, radioactive decay and carbon-14 dating. Okay. Again, trying to save us a little bit of time here. I do have a poster on this ready to go, so I'm going to more or less copy this poster while explaining this bit to you guys. Okay. All right, so you guys got this hanging from the ceiling, and I'm just going to copy this right here. Okay. So we got a set of axes. On the vertical axis, I'm going to do the amount of some substance. Sometimes it's listed as a concentration. And on the horizontal axis, it's going to be time, right? Could be seconds, could be years, or it depends on what we're talking about. Okay. So anything that's radioactive will decay into like something else, a different kind of atom, okay? And it will have an associated half-life. So if you start off at time 0 with some initial amount, I'll call it A naught to be the initial amount. Right? If you wait one half-life, call it T sub 1/2, right? Then now you're down to half of what you originally started with. Right? You let another half-life go by, and now you're down to 1/4 of what you started with. You let a third half-life go by, now you're down to 1/8 of what you started with. Right? And this halving process can continue like indefinitely, right? I'll just keep going. Right? Now this is an exponential curve, right, with a negative exponent. Let me write down 2 different ways you could describe this. I only put one on my poster, but I'll write you guys 2 different ways here. Right? So the more intuitive way is the amount that you have is equal to the amount that you started with times 1/2 to the power of the number of half-lives that have elapsed, which you can express as the time that's passed divided by T 1/2. Right? Yeah, I think it's more intuitive way to express that. The more like strictly mathematical way to do it is with the number E, right? You guys no, so A equals A naught times, and then it says, say in this bit, you say, you guys know E is like 2.71828. It's irrational, right? Kind of like pi is, right? So to the negative KT, right? And if you know the half-life of a substance, you can calculate what this K is. It's like some associated constant, right? But like here, I listed the numbers for carbon 14 on my graph over here, right? So carbon 14, for example, has a half-life of 5,700 some years, right? So whatever you start off with, if you wait 5,700 years, now you have half of that, right? And the part of this decay is decayed into nitrogen. That's what carbon 14 does. Right? And then the associated K value that would go with that, you can calculate it, but to like go from one to the other version of this, right? Like this K value, right? The unit would be like 1 over the time unit, in this case, 1 over years. Right? So let me list that here too. Carbon 14 has a half-life of 5,730 years. Right? Now, most carbon in the world is not carbon 14. Do you guys know what the vast majority of carbon is? Yeah.
13,
12. Yeah, there you go. Carbon 12, right? So it's like 6 protons and 6 neutrons. Right? That's by far the most abundant isotope of carbon, right? Carbon 12, right? All of us right now have a bunch of carbon in us. And again, the vast majority of it is carbon 12. But all of us right now have a small proportion of carbon 14. Now, why am I focusing on carbon 14? Like there are lots of radioactive elements, right? Isotopes, right? So why do I care so much about carbon 14? Because it's really commonly used in radioactive dating, right? For this reason. Anything that is organic has some proportion of carbon 14 in it, right? That will eventually decay into nitrogen, right? And as soon as a living organism dies, that process of maintaining that proportion of carbon 14 stops, and this carbon 14 starts to dissipate. So if anything is alive, there's some known amount of carbon 14 in it, like some proportion. Right? And suppose an archaeologist comes upon some old ruin and it has organic material. Right? Maybe we're finding like old animal bones or something. Hey, I wonder how old this is. And then you take it to the detector and it has half the amount of carbon 14 that it should have if it were alive. You could say, well, it's probably about 5,700 something years old. What if it has a quarter of what it should have? Oh, well, it's probably a little over 11,000 years old, right? You guys see that? And that's how you do carbon dating. Right. We're gonna do one more here and then wrap this up. Right. And the last one we're gonna do, and I should bump this closer to the standard model. I might in the future rearrange this list. 4 fundamental forces. So we got gravity, which gravitationally attracts. We talked about universal gravitation and orbital speed and gravity fields and stuff that back in fall semester. Right. We've also got electromagnetism, which you could guess, okay, electricity, magnetism, sure. How about chemistry? Anything is chemistry related. Well, we're talking about like interacting electrons, like valence electrons, so that too. But also anything is contact forces. Like how can I pick up this pen right now? Well, it's electrons pushing against electrons. If I drop it, what's the normal force on it right now? It's stopping it. So also, like anything that we talked about fall semester is really one of these two. It's either gravitationally attracting or electromagnetism also accounts for any contact force, tension in a string, like pushing, applied force, friction force. Those are all fall under the umbrella of electromagnetism. Now in quantum mechanics, we've got these 2 nuclear forces. So there's the strong nuclear force, which is responsible for holding atomic nuclei together. Like why would protons all want to hang out in the nucleus? Right. Well, scientists assign strong nuclear force for that. There's the weak nuclear force, which is associated with radioactive decay. So we've got these 2 nuclear forces. Right? You might even remember recently with relativity, there's a case made that gravity is maybe not so much one of these forces as it is an artifact of the warping of space-time, but classically it's considered one of these 4 forces. So there you go. You got 4 fundamental forces in the universe. All right, so let me get lights. You guys ready for lights? Lights. All right, just in time. So if you got up to that point in the journal, let's just end the journals right there. If you got everything, then you can turn it into the grade tray and I'll give you guys points. If you missed anything for any reason, if you missed a couple of these, or if you were absent, then you can find these videos on Google Classroom and bring it Friday. Okay. So you can either turn the journal today or Friday. Does that sound good? Okay. And I won't see you guys next couple of days. Right. Okay. You guys remember where you're going Wednesday, Thursday? I got some relocation information right here. All right. And that is a wrap. right, you guys have a great afternoon.